Okay, in this video we're going to begin section 5.3, which is the fundamental theorem of calculus. I'm going to let FTC represent fundamental theorem of calculus. Your book is going to do the same thing also. Now, the fundamental theorem of calculus is like the big result in calculus, all right? We're now ready to talk about that. There's also a part 1 and a part 2 of this, okay? Both parts are very important. So let's talk about the part 1 here. It says that if f is a function and it's continuous on a closed interval a,b, then the function g of x, which is the definite integral going from a to x of f of t dt, is continuous on the closed interval ab, differentiable on the open interval ab, and g prime of x is f of x. Okay, now what does this mean? Well, essentially, if I go down to the bottom here, the fundamental theorem part 1 is saying that if you integrate a function first and then differentiate the result, you're going to get the integrand, but in terms of x. Now the integrand is the function that is inside the integral here, right? F of t. So if I integrate that, find the antiderivative, and then I take a derivative, I'll get the integrand, but in terms of x. Okay? We can use the fundamental theorem to be able to check our answers when computing antiderivatives later, right? But I do want to go through a proof of the fundamental theorem. So here's a proof of that, and this is from the book. Okay, it says that if x and x plus h is not 0, okay, are two numbers that are in the open interval ab, then g of x plus h minus g of x. Okay, well g of x is this integral here. So like any other function, there's input values and output values. X is the upper bound, so I'm going to replace x with x plus h, okay, and then I'm subtracting g of x. Now, this first integral, I'm going to go ahead and split into two integrals at x. Okay, x is between a and x plus h. So let's find the area under the curve going from a to x, and then whatever that area is, we'll then pick up with where we left off at x, and we'll find the area under the curve from x to x plus h. That way we'll get the total area under the curve from a to x plus h. Okay, the second integral I'm leaving as is. Now these two integrals are just numbers, right? A definite integral is just results in a number, and so they're going to cancel there for me. And that leaves me with the integral going from x to x plus h of f of t dt. Now, that's g of x plus h minus g of x is this integral here. So if I divide both sides by h, again, h is not 0, then g of x plus h minus g of x all over h would be equal to 1 over h times the integral going from x to x plus h of f of t dt. Now I'm going to come back to this a bit later. Here's a picture of what's going on. I've got a function f that is continuous on some closed interval ab. Okay, so I've marked out a and b. There's no holes, there's no vertical asymptotes, right? And so because f is continuous on the closed interval ab, f would be continuous on any interval inside of ab, right? X and x plus h are two numbers that are inside of this interval. So of course f is going to be continuous on the closed interval x to x plus h. So by the extreme value theorem, okay, we talked about that in section 4.1. Remember, the extreme value theorem said that if you have a continuous function on a closed interval, the function has both an absolute max and an absolute min on that interval. Okay, so I'm guaranteed to have both an absolute max and an absolute min on this interval x to x plus h. I'm going to let f of u be the min, and I'll call that m, whatever the y value is, and I'll let f of v be equal to capital M be the max. Okay, and so I've indicated that here on my picture on this interval x to x plus h. So like here'd be the min, and here'd be the max. Remember, max can occur at an endpoint if it's an absolute max or absolute min. Now I'm going to let t be some number between x and x plus h. Okay, now knowing that t is between x and x plus h means that the y value when x is t is going to be some number between the min and the max. Right? F of t would be the y value for t, and that's going to be some number that has to be between little m and capital M. Otherwise, little m is not the absolute min, and capital M is not the absolute max. All right? So that's where this statement is coming from. Now, the next thing with this three-part inequality here, I'm going to go ahead and integrate throughout all three parts with respect to t. Okay, so I got the integral going from x to x plus h of little m dt less than or equal to the integral going from x to x plus h of f of t dt less than or equal to the integral going from x plus to x plus h of capital M dt. Now, little m and capital M are constants. When you integrate a constant, you're just taking the constant times the upper bound minus the lower bound. Okay, so that's what I'm doing here. I've got the constant little m times the upper bound minus the lower bound. And on the right side, I've got the constant capital M times the upper bound minus the lower bound. X minus x, those are gone. Little m is what I'm calling f of u, and capital M is what I'm calling f of v. Okay? Now the next thing I'm going to do is I'm going to divide throughout these three parts by h. So I've got f of u less than or equal to 1 over h times the integral going from x to x plus h of f of t dt, that is this guy right here, okay? And that is less than or equal to f of v. So what I had mentioned here in the middle, coming back to what I had done earlier, that is g of x plus h minus g of x all over h. Okay, so I'm going to go ahead and replace that in the middle part of this inequality. And now the next thing I'm going to do is I'm going to take the limit as h approaches 0 in all three of these parts here. Okay, well, the limit as h approaches 0 of f of u, that would be equal to the limit as u approaches x of f of u. Check it out. So from the picture, h is approaching 0. Okay, so this distance is shrinking if h is approaching 0. Now, as h is approaching 0, u would be approaching x. Okay? Now, the limit as u approaches x of f of u, that would be f of x. Why can I say that? Well, that's because f is continuous, right? We were told that initially in this theorem here, f is continuous. So what does it mean to be continuous? It means you can make a direct substitution for that number. There's no issues with division by 0 or a negative underneath the square root, right, or something like that. Okay, we're continuous, so you can plug it in. Now do the same thing on the other side. We got the limit as h approaches 0 of f of v. Well, that's the same as the limit as v approaches x of f of v. Okay, if I come back up to my picture, h is approaching 0. So this distance here is shrinking. Well, that's going to pull the max value, right? It'll change. And so v would be approaching x. Okay? Now the limit as v approaches x of f of v, that'd be f of x. Again, because f is continuous, you can directly substitute in that value there. Now, where in the world could I possibly be going on all of this? Okay, there's a lot going on. Well, I'm taking the limit as h approaches 0 of all three parts. So the limit as h approaches 0 of the guy in the middle, which is g of x plus h minus g of x all over h, that's by definition what we call g prime of x, right? That's the limit definition. And that also has to be the same value as the limit of the two outer expressions as h is approaching 0. That happens by the squeeze theorem, okay, since this function here is squeezed between the other two. Now, that's where I had to get to, right? I had to show that g prime of x and f of x are the same thing. Okay, that is the big result. That's part one of the big result. Okay. Now, in other words, as I mentioned earlier, if you integrate a function first, where the upper bound is x, and then you take a derivative, you're going to get back to where you had started with the integrand, whatever that is, but in terms of x. Okay? Now, there's a lot going on in this proof, I understand. Okay? But I think this proof kind of summarizes a lot of what we've done throughout the course. There's, I mean, we're talking about continuity, differentiable, integration, mins and maxes, the extreme value theorem, the squeeze theorem. You know, there's a lot going on. This is, you know, the end result. Okay, this is one of the big results here, part one. Let's take a look at some examples of where we're using the fundamental theorem part one. Okay, so here's an example. Find the derivative of the integral going from 0 to x of the square root of t squared plus 3 dt. Now, f of t would be the square root of t squared plus 3, and that's continuous on the entire number line. Doesn't matter what t is. When you square a number and you add 3, you're never going to get a negative. Okay, and that'd be the only thing that I care about here with the you know, the square root sign there. I've got a continuous function, and it's differentiable everywhere. So by the fundamental theorem part one, when I take the derivative of this integral, I'll get the integrand, but in terms of x. So my answer is the square root of x squared plus 3. Okay, now in the theorem, the lower bound can be any number. Doesn't matter. Okay, it could be 0, it could be 3, it could be 1, it could be whatever. Okay, so here's another example. Suppose that I were to find h prime of x. Well, the derivative of an integral is the integrand, but in terms of x, the upper bound. So all I do is I just replace t with x, and so h prime of x is e to the x squared minus x. That's the end. Okay. Now I feel like a lot of what we're doing here is notational stuff. Okay. Like everything else that we've been doing, pay attention to notation, because I'll have people write dx when it should be dt, and I'll have people be sloppy with like the integrals, you know, notation and derivative notation, like they won't be writing things down correctly. I feel like a lot of what we're doing here is, you know, writing things down correctly. So make sure that you understand that part of it. Okay. Here's another example. G of x is the integral going from x to 1 of cosine of the square root of t dt. What is the derivative? Well, in the theorem, x has to be my upper bound. Okay, and I don't have that here, but I can switch the bounds, right? We saw a property in the last section that allows us to switch the bounds if we throw a negative in front of the integral. Okay, so I've done that. Now I can just plug in the upper bound into the integrand. And still, of course, I still have the minus there in front. So negative cosine of the square root of x would be the derivative of g with respect to x. Now we're calculating derivatives, okay? So one element of differentiation that we had looked at in chapter 3 was the chain rule. Okay, the upper bound is not always going to be just plain old x. All right, it could be some other expression in terms of x. Okay, or it could be a constant where you got to be, you know, there's work to do. It's not just plug in the number and go to the answer. All right. So here's another example. Suppose that we have y equals the integral going from pi over 2 to x cubed of cosine t dt. Well, because my upper bound is not just plain old x, I don't just plug in the number and call it, you know, cosine of x cubed. If I did that, I'd have the wrong answer, by the way. All right. In this situation, you're going to use the chain rule in the fundamental theorem part 1. I'm going to let u be the upper bound, x cubed. All right. So if I want to take the derivative with respect to x of this integral here that was given, that would be the same as the derivative with respect to u. U is the upper bound, but then remember, you got to complete the chain rule. You got to multiply by the derivative of the thing that you're ignoring, which is the derivative of u with respect to x. Okay. Now, by letting u be x cubed, then in this form, my upper bound is just plain old u. So by the fundamental theorem part 1, I just simply plug in my upper bound into the integrand. And so I've got cosine of u, but then, like I said, I've got to finish the chain rule. I'm multiplying this by the derivative of u with respect to x. Well, the derivative of x cubed would be 3x squared. U is x cubed, so my answer would be cosine of x cubed times 3x squared. Okay. Basically, in the case of where you have a situation where the upper bound is not just x, you're going to plug in that upper bound and then take the derivative of that upper bound. That's essentially what I did here. Okay, here would be the best behind-the-scenes part of it, but I'm using the chain rule. Okay, let's take a look at another example. Suppose that I want to find the derivative with respect to x of the integral going from 1 to the square root of x of z squared over z to the 4th plus 1 dz. Okay, well, the upper bound is not just x, so this would be another situation where I'd want to use the chain rule and the fundamental theorem part 1. I'm going to let u be equal to the square root of x. Okay, and so when I take the derivative of this integral with respect to x, I'd be taking the derivative with respect to u of the integral going from 1 to u of z squared over z to the 4th plus 1 dz, but then I got to finish the chain rule. I got to multiply by the derivative of u with respect to x. Well, let's see here. So my upper bound being just u means that now I can plug in my upper bound into the integrand, and I got to finish the chain rule though. Okay, I got to multiply by du dx. Now u is the square root of x. Okay, so I'm replacing that. And then the derivative of u with respect to x, well, that's going to be 1/2 x to the negative 1/2, or 1 over 2 root x, using radical notation. When I simplify, okay, I'm going to have x divided by the square root of x, that's the square root of x. 2 will be kept in the denominator. The square root of x to the 4th, that's same as x squared. Okay, so you're going to have 2 times the quantity x squared plus 1 then in the denominator. And that would be my answer then. All right, so again, you'll notice that all I've done is I've replaced the upper bound in the integrand, but then I got to take the derivative of that upper bound, okay, in order to finish the chain rule. All right, again, I will re-emphasize that I feel like a lot of what we're doing here is the notation part of it. Okay, make sure that you're writing things down correctly, and that you understand what we're, what it is we're writing. Okay, and we'll be using the fundamental theorem part 1, to be able to check our answers, because that's really what it's saying. If you integrate a function first, you can check your answer by taking a derivative to get back to where you started. Okay, well, that's something that I think we already know, right? When it comes to an antiderivative, we talk about antiderivatives in section 4.9. If you calculate an antiderivative, you can always know if you have the right answer by taking a derivative. Okay, I mentioned in that section, derivatives are going to be kind of phased out a little bit here, but not completely. Okay, we still have to know how to check an answer. Okay, so that's derivatives, don't go away completely is the point. Now, there is also a part 2 of the fundamental theorem. Okay, and I'm going to talk about that in the next video. The part 2 is also extremely important.